Okay, let's actually continue. Uh, so there's this very interesting blog. I think we also saw this blog at some other point. I think when we were talking about attention, there's a really good, you know, summary or a good read through. You may not understand every part of it, but it's a good idea to get a gist of what's going on. So it's on the web page under this particular lecture's materials. So have a look at. Uh, they don't talk about, I guess, A/B testing, but they talk about this exploration versus exploitation dilemma, um, and different strategies. So we have looked at epsilon greedy, we've looked at UCB1, we'll look at Thompson sampling now, okay? And I think it's a good exercise to look at it. Um, so let's talk about Thompson sampling. Okay, sorry. So the idea is very simple. Okay, so in epsilon gradient UCB1, what were we trying to do? We were trying to spend some time on those actions or those choices which were probably not the best with given the current information so far. Okay, given the current information just means the current empirical statistics. Mu hat one, mu hat two, mu hat three. These things change as you get more data. But given the current information, you also want to spend not just find the best guy, not be just greedy, but do something else, which is exploration, right? So Thompson sampling also tries to balance this exploration exploitation trade-off by doing something in a Bayesian way. Okay, so what is the Bayesian way? You always think of some distributions. Okay, so not what we will do is that there's going to be each arm has a true mean reward value, right? Mu1, mu2, mu3. Okay, let's say in the 3 case. In fact, in that example, it's 30.3, 0.4, 0.2. Okay, this is the truth, right? This part. Now Tom sampling says, okay, there are some true mean values. I care about doing in my I care about regret. Regret is all in terms of expectation. I don't know the true mean values, so I'll maintain a distribution over these mean values. Okay? So let's say the mean values themselves. I mean, in that example, it was 0.3, 0.4, 0.2. Okay. Let's say they're between 0 and 1. So I can always assume, oh, maybe the mean value for the first guy is a uniform distribution because I don't know what is the mean value. And maybe for the second one also it's a uniform distribution. And for the third one also it's a uniform distribution. By the way, this distribution is not related to the true underlying distribution of the arm itself. Okay, those mu's are not related to this belief that I have on the mean value. It's just a belief on the mean value. That's something I am thinking about. Okay, I as an agent or a platform or a decision maker. Now, so that's a uniform triad, or basically assuming that my belief is that each of the mean values are has a are basically mean zero point 0.5, and it's basically a uniform distribution. Now, what I do is try an arm. Okay, try an arm, and how will I try an arm? Let's say, so for that I'll tell you at the general round T what we'll do. At round T, it may not be uniform. At round T, I may have a different belief on what the mean rewards are. Okay. Those beliefs I'm just representing here as pi subscript I comma t. I just represents the three arms I1, 1, 2, and 3. Pi represents a distribution. Okay, on these mean values. Okay, think of, so what is the simple distribution on 0 comma 1? Beta distribution. Okay, so beta distribution is a distribution with support between 0 and 1. So just think of pi being, let's say, beta distributed. Okay, and so I have three beta distributions. Okay, one for the first arm, one for the second arm, one for the third arm. What I'll do is sample from each of these three beta distributions. Okay, sample as in I'll get one number. Okay, three numbers I'll get total, and then I'll just pick the arm which is the maximum of these three numbers. Okay, so remember this step looks very similar to the UCB step. Okay, except this part was that the mean empirical mean plus some bonus thing. Okay, so what's happening is that I'm maintaining a belief. The beliefs represent how good an arm is, and from there I'm sampling, and the sampling is kind of going to capture some exploration aspect of the problem. Okay, because if I maintain beliefs, I can always take the mean values of the beliefs, as in mean values of distributions. Whichever mean is the highest, I can always play that. Okay, that's just exploiting. Okay, exploring is when you sample, because even if the mean value is higher, because I sampled, sometimes I can get a value less than the mean, right? So that's the idea. How many of you did not follow that? It's, okay, let's look at the picture. So time. Okay, let me just do it properly. So let's say I have so um, let me actually do it this way. So website 1, website 2, website 3. At the beginning of time, t is equal to 1, t is equal to 2, t is equal to 3, and so on. Okay. So let's say at the beginning of time, I don't know what the mean value is. So I'm going to assume a uniform distribution, okay, between 0 and 1. These are all uniform distributions. Okay. So why does it look like this? Is the y-axis is the probability mass. Okay, it's a continuous distribution between 0 and 1. So it's uniform because probability of any number is the same. Okay, that's uniform distribution. So because they all look the same, I'm going to sample one number from each one at this point. Okay, this is my belief of what the mean values were. So mean values were 0.2, 0.4, and 0.3, 0.4, and 0.2. Actually, let me write it here. 0.3, 0.4, and 0.2. These numbers I don't know. Okay, just like before. I'll assume that, oh, it's some number, but I don't know what number it is. Initially, I don't have any data, so I'm going to assume belief to be uniform. Okay, but now I need to take an action, right? At this point, I need to try something. So I'm going to get a sample from this guy, this guy, this guy. Okay, maybe from that sample, let's say the sample is some number here, some number here, and some number here. Okay, then you can see that maybe this number is the highest, right? You can see among these three numbers, maybe this number is the highest. I'll play this arm. Okay, because I played this arm, and let's say my feedback is Bernoulli for simplicity. Okay, Bernoulli just means I played that second website and they clicked or not. Okay, I see that, and because of what is called beta Bernoulli conjugacy. Okay, I think we talked about conjugacy at some point in LDA. I don't remember, but maybe we'll discuss conjugacy again. So I'll see maybe they clicked. Okay, if they clicked, I need to update my distribution. It will become something like this. Okay, between 0 and 1. This is a beta distribution. Okay, so and the other two remain the same. Okay, 0, 1, 0, 1. So other two distributions remain the same. This guy becomes a beta. I mean, because it was I played this arm, the guy actually clicked, so I need to put more mass on towards maybe higher reward. Okay. So, but at this point you can be exploiting by just saying, oh, mean value is somewhere over here, mean value is here. Maybe I should always play two. But that's not the case. Okay. We want to exploit as well. So again, we'll sample. Every round we'll sample. Okay. And if we sample, it could be that most likely I'll play probably 2, but with some probability I may get a sample which is on this part, okay, which means that I may get to play 1 or 3, and so I may be able to change these distributions. Okay, so eventually, maybe t is equal to maybe 1000. These distributions will concentrate. So this one will be like something around 0.4. This guy will be something around 0.2. Okay, this is between 0 and 1, 0 and 1. And this guy will also be between, let's say, something like 0.3. Okay, so that's what's eventually our beliefs will become sharp around the actual mean value. Okay, if you okay, let's say you did not take action based on sampling from this, but you had beliefs like this and you just did round robin. Okay, you just do round robin also, you'll get the same thing. Okay, they'll concentrate, but what you lose is you lose a lot of money in the process. Okay, that's not what you want. Okay, so you want to exploit. So if you only do exploration, it's also called a pure exploration problem. Also, if you only do exploration, you can go from these distributions to things which exactly concentrate around those. But that's just the learning problem. But here we care about decisions and how well they do as well. Okay, so that's what's going on here. Yeah.
You said it just to clarify though, we make our decision about which one to take based on whatever has the highest view.
Yeah.
At any of the 3.
Yeah.
And then that shifts around.
Yeah. So here, as I said, we got some samples. Don't worry about this particular form. At any given point of time, I'll have some belief. Okay, may not be uniform, right? I'll do some sample. Okay, and I look at the one which has the highest number, and I play. The sampling part is letting me explore. Okay, if I was just taking the mean values, it will not let me explore.
So we always sample all three and then we pick
Yeah.
the highest.
Yes. So we're maintaining beliefs. Beliefs just means distributions, and we'll pick, not the mean values because those numbers are not sampled, so it'll always be like exploiting. And so we'll sample to kind of do this exploration. Okay, that's the intuition. Is it more clearer now?
When this process, even after like infinite time period, might
Yeah.
happen that in between you will still, after like doing so many of answers,
Yeah.
it's still possible that you might be showing the website which is not the best one because you still keep sampling, right? Even
No. I mean, if the samples are like, think of like getting almost a delta distribution here, delta distribution here, delta distribution here. You'll never get a sample. You'll never get a sample such that this guy is not. You'll never get a sample where something else is higher than this guy. If think of like really concentrated distributions, you know, eventually. Okay. Is it clear? So that's what's written in text here. It's actually a really old algorithm. Gonna be a century pretty soon. Okay, in 14 years or something. So I don't have too much time, so I'll skip conjugacy property. But this is something that you can try reading up. This is not very critical here. Okay. But conjugacy just helps you. So here's an example. If I maintain a beta distribution belief, okay, and my likelihood, okay, is going to be Bernoulli, then the posterior distribution tends to be still beta. Okay, it's like saying I want to apply Bayes rule. When I apply Bayes rule, where the likelihood part is Bernoulli distribution. I mean, given the parameter, the observed thing is Bernoulli, and the parameter has a beta belief on it, then the posterior belief on the parameter is still beta. Okay, that's conjugacy. Okay, that means beta and Bernoulli are what is conjugate? I think beta is conjugate to the Bernoulli model. Okay, it's just some sort of a nice computational trick that can be used. Okay, so it's not very critical right now, and I'm going to drop all this Dirichlet stuff. So beta and Bernoulli are one-dimensional things. So if you have Dirichlet is something that we saw in latent Dirichlet analysis, right? Latent Dirichlet allocation, LDA, where Dirichlet was a distribution over the simplex of probability. Like if you draw a sample from the Dirichlet distribution, you would get a probability mass function of 3 dimensions or 5 dimensions or something like that. Okay. So there is also the conjugacy there as well. If you have a Dirichlet distribution and a categorical likelihood model, then the posterior is also Dirichlet. Okay. It's just computational trick, but kind of very useful when you're doing Bayesian models. And these are approximations of things, model choices that you can use to speed up computation and so on. But I will drop that. So in the remaining time, I actually want to. So we have seen two, 3 methods. Okay, to understand this blurring between estimation and decision. Okay, for us, the estimation or forecasting was very simple so far. There was no features. All we cared about the mean performance of the output, mean performance of the label, or mean performance of the decision. There are 3 decisions, 3 labels. We just want to know this marginal probability only, like something like just the outputs, right? Now, what we're going to do is actually look at a situation where we don't even have to assume any stochastic model on the reward process. Okay, in the sense of if I take option A, I said 30% of the time people will click on my whatever website, and if I take option B, 40% of the time people click. Okay, I mean 40% of the time people click just means a Bernoulli distribution where they flip the coin. 40% of the time it's heads, and therefore they click. Okay, that's the model. There was a distribution associated with each choice. Okay, now what we'll do is we'll drop the distributional assumption. Okay? We don't even need it. So it could be, the people may not be behaving according to a distribution. They may not be flipping coins. They may be, doing some, following into some decision rule or their own mental process, which is going to be, you cannot really model it, right? It could be adversarial as well, in the sense that they may choose it to kind of mess up your estimation, for example. Okay. Um, so we can do that. And the way we do that is as follows. This is a slightly different model. It's called an adversarial model. Okay, I think at the beginning I said it's a stochastic multi-arm binary setting. The stochastic part was trying to say that each arm has a distribution associated with it, from which you get a reward. Okay, like for example, a Bernoulli distribution, you get a click or no click. Okay, now there's no distribution associated with each arm. Okay, you don't have to assume that. And so then, how do I give a reward every time I take an action? Okay, there has to be some model, some description of how the environment is going to give me a reward. So the way we do it is the following. Every round, you pick an action, one of the choices, website 1, 2, or 3. And every round, the adversary or some non-stochastic whatever environment, in this case, also picks 3 numbers. Okay, click, click, no click, let's say. It already pre-decides. It doesn't see your action. And then you reveal to information, it's like click, click, no click, and I picked the second one, therefore it's click. Okay, so that's the model here. And that's what's written here. Adversary selects what's going to happen. Let's say click, click, no click, and then player selects the action. Let's say 2, and let's focus on the last point. Player only sees what happened. Okay, it clicked. So player showed option 2, and what happened? It clicked. They clicked. There is another setting which is actually I can map it back to supervised learning, where we also know what would have happened if we had shown website 1 and 3. Okay, that's like a counterfactual question. Counterfactual just means something which did not happen, but what if I had shown 1 or 3? What would have happened? Because in this model, the adversary or the environment, or in this case the user, is already pre-deciding. If you show me website, I mean, it's not realistic, but he's already saying, if you show me website 1, I'll do what? I'll do this. I'll do that. I'll do that. Okay? Click, click, not click. Even before you tell me what you're going to do. Okay? So because the adversary chooses all these numbers, okay, click, click, no click, let's say 1, 1, 0, there's a variation called the full information setting, where you do an action, but you also get more information. You would also get, what if I did this, whether they would have clicked. What if I did that, they would have clicked. It's a little bit unrealistic, but actually in classification problems, okay, not online learning, but in classification problems, you do get that information. For example, there's an image, let's say, you say there's a cat in there, but some expert, in this case environment, can say, it's not a cat, it's actually a dog. So it's not just that you knew whether your cat prediction was off, but you also know which prediction would have been correct. Okay, maybe your fox prediction is going to be wrong, your dog prediction is incorrect, is also revealed. Okay, that's called a full information setting. Okay, just it's just a question of how much information you know. Classification is a good example, where I say this is the class. Either the expert can say, this is not the class, or they can say, this is the right class. Some other class is the right class. Okay, some other class being the right class is more information. That's called full information here. Okay. So here's the algorithm. Okay. So see, most of this lecture is not about like understanding the nitty-gritty details of the algorithms, but the intuition, both with epsilon greedy, UCB, Thompson sampling, and now EXP3. It's the intuition that should be clear, and the problem setting should be clear. Okay. So we still have k options, 3 options here, 3 websites, 3 variations. What we'll do is we'll maintain a number on each website. Okay, it's like again a belief, but it's a belief. This is not like a uniform distribution. It's like, here's a score for website 1, here's a score for website 2, here's a score for website 3. Okay, and at each time t, I'm going to pick an arm, but I'm going to randomize my choice of picking. Just like in Thompson sampling, I'm going to randomize. But how am I going to randomize? I'm going to randomize according to distribution, which is going to be, whatever scores I have, I'm going to normalize them first. That's this term in the center. Okay. This term in the center. Normalize those scores. And once I normalize the scores, maybe arm 2 has a really high if I normalize the scores, let's say for the first arm it's 30%, second arm it's 40%, and third arm it's again 30%. They have to sum to 1, right? This a divided by sum of a plus b plus c, they all have to sum to 1. Then what I'm saying is you pre-multiply with a number, with a let's say a large number, and you post multiply with the same parameter but divided by k. Okay. So why am I doing that? Is to ensure that if the scores are low for some arm, okay, some action, some choice, then this guy is an offset, constant offset. Okay, gamma is some fixed number. Let's think of it as zero point 0.1 or something, and k is a fixed number. They only have 3 arms. So this is like some sort of this probability number cannot go lower than, for example, this guy. It's 0.1 by 3. Okay? So you'll always at least try this other arm, irrespective of what the score eventually becomes. Okay? That's all. This gamma fix is just to ensure that you'll always try the other arms at least by this much. That's all. Okay. So the main all the action is kind of happening here, okay, inside. Or in other words, what I'm saying is this, gamma is ensuring some amount of exploration, basically. And any given round, there is some at least this much probability you'll try some other arm. I mean the worst arm, for example. Okay, that's all. Now let's focus on this guy. These are scores I'm maintaining. Let's say I pick some arm, okay, some action or some website, and I show that to the user. Okay. I show that to the user may click or not click. Okay. Once they do that, I have to update my information, right? I have to update my weights, the scores. If they click, let's say I show arm 2 and they actually click, I should probably like increment the score, right? I mean, that's kind of very natural thing to do. Very natural algorithm, right? So that's what we do. And it looks messy, but all it's saying is whatever was okay. All it's saying is the score is just some exponentiated sum of the clicks. Okay, it's just saying, oh, you played arm 2 from the beginning of time. Whenever you played arm 2, was there a click or not? If there is a click, x is 1. If it's not a click, x is 0. Okay, but there's a slight change. Okay, that's not x itself, the click or not click itself, but it's click divided by the probability that I chose arm 2, whichever arm that is. Okay, so okay, I'll talk about why we are doing this a little bit. This is not very critical, but all I'm saying is the loop is just very simple. Okay, maintain some scores. Okay, whenever you have scores, whenever you need to take a decision, do a normalization and pick an action according to that normalized PMF. Right, it's a distribution over the 3 arms, P1, P2, P3. You get some and take that action. You get some reward, right? X tilde for that, X for that round. Okay, and just increment, just update the score like this. Okay. So it could be made incremental. Okay, WTK can be written as a WT minus 1k times e to the power eta times the new information that is revealed. Okay. So anyway, this is a very simple formula. Given the clicks so far out of all the times I've shown, W is incremented this way. Okay. This is not very critical. There could be some other ways. You can just add, for example, right? That is also one way to increment the scores. So this is it. This is the algorithm. And this algorithm, people have shown that this algorithm works even when I don't assume any distribution on the arms. Okay, so there's no mu's that were there before. Okay? Even if there's no mu's, this algorithm works in a sense of regret. Okay? People can show that if you follow this algorithm and whatever sequence of arms you pull, that's not too bad compared to the benchmark. Not too bad compared to knowing the best arm in hindsight. Okay. Now, best arm in hindsight is there's no mean, there's no fixed, there's no means here. So you have to figure out, oh, given this, all the arms, these are the rewards. You need to figure out which arm is the best. Okay, you need to know that number. I mean, you as in like the algorithm doesn't need to know that, but the algorithm is going to compare against all these numbers and then which number has the highest, which arm has the highest number. So actually, let me show that by a very quick picture so that you can understand. So there are 3. So x1, x2, x3. Okay. So these are the responses in time is equal to 1. Okay. So let's say click, click, no click, click, no click, click, 0, 1, 0, 1. 0. Okay, let's say something like this. Okay, so these are clicks, but you would not observe all of this, right? In a round T, I would play something. Let's say I play 2. Okay, I would only observe this one. Okay, in next round, maybe I played something else. Maybe I observe this guy. Maybe I observe this guy. Maybe I observe this guy. Okay, right? But what is the best arm in hindsight? Best arm in hindsight is the one with the highest reward, right? This guy with 3 ones. Okay, so the benchmark is this, and your algorithm did these guys. Okay, algorithm got, oh, it actually got 3 points and it's 3. So in this case, regret is 0. But so that's the benchmark. Okay, slight difference from the previous stochastic setting. Um, yeah, here I'm just showing that in this case the dependence on time is square root n instead of log n. So I think it's not a big deal, but because we are in a tougher setting, we are making less assumptions about the arms, about the rewards. There is no distribution. The dependence on time, as we like regret has kind of increased, so to root n instead of log n. Okay. Yeah. So I don't think I have anything more to say here. So let's move forward. Uh, yeah, here I'm just showing the W's, the weights. Okay, in this case there are 10 actions, so the 10 weights. You can see that the weights are going down for the ones which are not relevant, and the ones which is kind of the right arm. That guy's weight is kind of increasing over time. Okay, so that's what the algorithm. You can code these up. These are very simple strategies. You can code these up, and in fact, in that blog post, they would show you the Python code as well. So and also there's a link to GitHub repo which does these as well. But it's just to get an intuition of, so as I said, I keep repeating, but this moving away from just supervised learning or just learning or just estimation to estimation while making money. Okay, that's something which firms care about, right? You can't just do experimentation and make a lot of users unhappy. Like a good chunk, 50% of users will be unhappy if you make a breaking change or something which is like not good, right? So you want to kind of cut down your losses. That's what we are doing here. Any questions about EXP3? Okay, so now actually I'm gonna move to now I'm gonna introduce features. Okay, so far it was just oh, there is no feature, but I still need to figure out what is the performance of each action, each decision. But now let's say users come with features. Okay, so the first user comes and they are they work in the mining industry, they are male, and the question is which website you should show. Same question, but now I know this additional information. So the decision space is the same, 3 websites or whatever variations of my website, and now I have context. Okay, context is just a feature vector here, and so you can think of it as a classification problem. Right? Given a context, I just need to map it to 3 labels or 3 actions. You can always solve it as a classification problem if you had the data, but to get the data, someone must have decided what to show, right? So it's somewhat of a it's a biased data in the sense that it's only telling you for this context somebody did this and this is what the reward they got, but it doesn't tell you for that data if you did something else what would have gotten, what would you have gotten. Okay? So there is that aspect of the problem. So let's go back. So MSN. So user arrives, they come with a context, and you choose one of the 3 websites, and user responds. Okay, maybe clicks on something or not. Okay, and your goal is to again maximize the total reward. Okay, so maybe the total clicks over the period of 1 week or something. Okay, and again the assumption is that currently for this lecture the assumption is that what I show the first user, one user, let's say the context is something they're happy and they're seeing the website, has no influence, and I show a bad ordering of articles and they're not happy, doesn't influence the next guy coming in. Maybe they're still neutral. Okay, I'm just saying that there's no relation between one context and the other. Okay. So I mean in this case basically saying no carryover effect from one interaction to the next. That's kind of the assumption so far. But we will look at more realistic assumption when there is a carryover effect. Users being exposed to something, a recommendation right now, like let's say you're opening Netflix, right? Recommendation that you're seeing right now in the first minute to the recommendation you're seeing in the 30th minute. Maybe again you open the web page to go back to the main screen. there's going to be some state, right? I mean, first maybe you were shown all comedies, and then you suddenly are seeing all musicals or something. There's some relation, and that's gonna users may perceive it differently based on what they saw before. Okay, and that is captured using reinforcement learning. And in fact, we saw at the beginning of the lecture this AlphaGo achievement as well as video game playing achievement. They require one screenshot of the next screenshot. They're not independent. That's all I'm saying. Or one state of the game board in the game of Go, and the next board they're not independent. Okay, there's dependent on the context is related. Okay, but anyway, so now let's come back to contextual bandit problem. Every round we get a context. We want to find the best. So what we want to find is not just the best action. Okay, so in a multi-round bandit case, there was a single best thing that you could do in hindsight. Okay, always show website 2, or always show always have the search bar at the top or the bottom. Okay? But here we want to find a policy. Okay, now use the word policy is a technical word here. It's a mapping. Okay, it's a mapping from context to actions. Okay, so if you are coming from supervised learning world, the word policy just means that function, the neural network, going from a feature to a label. Here it's a context to an action. Okay, it's pretty much the same. And of course, you may not see the same context couple of twice. For example, there are some issues like that, and different from bandits, which we saw in the previous half an hour or so, or an hour or so. There is no context previously, and we are finding a single best thing. Okay, there was no policy there, and policy means maybe it was a constant policy, constant function. So, what is the benefit of context? So here is an example. Okay, so let's say we have 5 ads. Buy pet lizards or 1-800 petunias and so on, and let's say we have 4 policies. Okay, so we have 5 ads and 4 policies. Okay, so ads are like those actions. Okay, so you need to show ad 1, ad 2, or ad 3. So those are the same as the decisions, actions. But there are 4 policies. What do? Given a user profile, they'll say, oh, show ad 1. Given a user profile, so 4 different policies could show 4 different things, right? Maybe the first policy says, oh, for this user profile, show ad A1, which is buy pet lizards. And for maybe the second policy for the same context says, oh, actually show A3, which is cheap MP3 players. Okay, so policies just differ by, I mean, if they exactly say the same thing, they're not 2 different policies, right? So they differ from what actions they suggest for the same context. Okay, but let's say there are 4 policies. Okay, now because now they're policies, because they're now context, I want to kind of import the idea of exp3, the algorithm, to this setting. So I can think of, okay, since I have policies and I want to figure out the best policy, now the problem is about figuring out the best policy. Maybe I can think of these policies as arms rather than the original actions A1 to A5. Okay, I have four policies. Okay, I can think of that, right? Because I can think of 4 policies. I just choose a policy, and the policy says, oh, in this context, do this, right? So it's quite natural. And so let's say in round T, the policies recommend the following. Okay, which is the policies are represented as using the letter E. Okay, so given a context, I'm not writing the context. Maybe you call it X if you want. So E of X, E1 of X is saying, oh, choose action A2. E2 of X is saying, oh, choose action A2 again. E3 of X is saying choose action A4, and E4 of X is choosing action A4. Okay, and so remember in exp3 I was maintaining a distribution over my arms. Okay, I have 4 policies. I'll maintain a distribution, or maintain not a distribution. Maintain 4 weights. Okay, on the 4 policies, right? So let's say weight 1 is 10, weight 2 is 10, and weight 3 and weight 4 are 5. Okay, so let's say total weight is whatever 30. Let's say, and now remember there was a normalization going on, and maybe I'll pull an arm. In this case, let's say I chose E1. Okay, by sampling from the weights, and then since I chose E1, then because of this context, E1 is suggesting A2. I'll just show A2. Okay, that's all's happening in this slide. So I showed A2. Okay, in ex3, what it does is it says, okay, I showed add A2. Maybe the user clicked on it. Okay, the user with that particular context clicked on it. Okay, the exp3 just does maybe excess of E1 is just a click or no click. Let's say it's 1 or 0. S is just a time, okay? Maybe clicks or not, divided by the probability with which I chose that click, chose that arm, that action, that arm actually, in this case, a policy. Some normalization, okay? It doesn't matter, so don't worry too much about this. This is for, I can explain it later. So I have some renormalized reward that I observe, and then I just update the weight for that policy, and every other policy is not updated. The same weights carry through. That's the whole point, right? I mean, things that you did not try, the weights carry through, and the thing that you tried, you got a reward or not got a reward, that weight gets updated, okay, in EXP3. And the question is, what is the benefit of the context? Okay, so far, if you just think of policies as arms and just maintain weights, it's just EXP3. It's not really taking into account context information at all, because policies are fixed. If you get a context, the policy literally tells you what to do. So you're not really learning anything. Okay, I mean you're learning, but not really exploiting the value of context. Okay, and now I'm going to tell you an example of how to exploit context here. So what we observe is that E1 was suggesting action A2. E2 is also suggesting action A2. Okay. So I took action A2, and maybe the user clicked. Okay. If the user clicked, then of course E1 was a good policy because it kind of, for this context, gave me the right thing. Good ad, and that got clicked. But E2, if I had chosen E2, that would also have led to the same action, and therefore it would also have gotten a click if I had chosen E2. Okay, so because it got clicked, I kind of update the weights of both these guys. Okay, that's the advantage of context and caption. Okay, is it clear? That's all. I mean, there's not much. Huh? All I'm saying is there could be multiple policies which all lead to the same action. Okay, so I have a distribution or policies, right? Not distribution. I have a distribution because I have weights and I normalize it, so I get a distribution of policies. I pick a policy, and the policy is suggesting add A2, right? And maybe it got clicked, so it's a good policy for that, good action for that context. Okay, so that this good policy at least for this context. But I also know that if I had picked some other policy, that also in particular E2, that would also have led to the same ad, and therefore it would also have gotten clicked. Okay, so although I got only one observation, I'm kind of using the fact that there are other policies which would have suggested the same action, and therefore they should also benefit from this feedback. Okay, I got this feedback of click. Okay, only not just the policy E1 should benefit from that feedback that it's good, but all the other policies which also say the same, take the same action, should also benefit from this click. Okay, there is multiple use of data going on. The feedback is getting propagated to improving the estimate of multiple policies which all suggest the same action. Okay, instead of just the policy that suggested that action, just one policy. Okay, so that's like a benefit of context. Okay. And that's literally what we've written here. The algorithm looks like the same. So this is a policy, generic policy 5. It's not the 3.14 or whatever. In a set of policies, in our case it was 4. We initially have weights. Since there are 4 policies, W1 is 1, W2 is 1, W3 is 1, W4 is 1 number. And for each round, I'm going to observe a context. That's a feature vector, okay, or image or whatever. And for each of my 5 actions, in this case there was 5 ads in that example, I'll find a distribution over these actions. Okay. This is just a different way to do the same thing. What I said. What I'm going to do is, can I look at the weights? Okay. Of all those policies which suggest action 1, I'll add them up. Okay. That's the net effect of me choosing action 1, right? And then for action 2, I look at all the policies for this context who suggest action 2. Add up their weights. Okay, that's the weight for action 2. Okay, for action 3, same thing. Add up all the policies weights, those policies which for this context are going to suggest that action. Okay, add up those weights. Okay, that's what this is. Sum over all policies. If the policy suggesting action A, then add up the weight. Okay, you can do that for each action A. Okay, and divide by the weights of all policies. So the denominator is just a large number, whatever it is. Okay. And the usual. So last time I think I explicitly wrote gamma and 1 minus gamma and gamma by k. You can just add the same thing. Okay, just think of this as 1 minus gamma and gamma by k or something. Okay. In fact, I have a expression here, but just some constant. Okay, it's something to do with the size of the policies, the number of policies, and k and time horizon. But some constant here. Okay. Why is this? Again, this addition is to ensure that all actions have at least some probability of getting picked. Okay, you want that exploration. Okay, so all these problems have to balance exploration and exploitation. Okay, so that's the key. And now since we have a distribution, draw an action. That's simple. But once you draw an action, you get a reward as well. So right now, slightly notation change. It's reward is RT. Okay, some reward, maybe click. Let's say. Once you get that click, then for each policy that suggested that action. So if that policy suggested that action, then I'm adding, I'm improving the weight. What was the previous weight? Plus e to the power something. Okay, e to the power something depends on r. So, right, for all policies which suggested that action, I'm gonna add up. I mean, e to the power something is always greater than 1. Okay, I mean, as long as the numbers are positive, and these in this case, if they are positive. Okay. So I'm increasing the weight for all those policies for which all suggest the same action if it clicked. Okay, so that's what's going on. Other policies, they are all the same. So what I just explained previously. Okay, so this is exp4. I don't think I have a simulation for this one, but this is the one where there's a context feedback. So context comes. I take some action. I'm kind of propagating that information to other policies which would have suggested the same action. Okay, so there's kind of a more efficient use of feedback than just thinking of policies separately and just updating them. Okay, that's exp4. It's a very inefficient algorithm. Okay, if there are if there are 4 policies and 5 actions, if there are 4 policies, then it's just four weights. But if there are 5 actions and contexts, let's say there are 20 contexts, then there are too many. Each context can have 4 different choices, right? So it's 4 to the power 20 different policies. Okay. So in a sense, all I'm saying is, even if you have finite number of contexts and finite number of actions, there's going to be some explosion in the number of policies that are possible, which is not good. But modulo that, this is a decent algorithm. Okay. Any questions about this part? Okay. I think it takes time to understand this, but as I said, there was a huge delta in this class compared to all the stuff that you've seen before. In the sense of, you saw supervised learning, batch data so far. Now we are always talking about, we have added an additional objective, which is we don't want to just learn simple things, learn just estimators or whatever they are, but also earn money, as in not lose, because of our bad decisions sometimes. We want to learn and earn. Okay, exploration, exploitation. So in the larger scheme of things, here's a picture, and this is pretty much the last slide. In bandits, we just have actions. We ignore context completely. We have, let's say, website 1, 2, and 3. We want to keep showing. We want to figure out which is the website that we should always show. Okay. If we show website 1, there's some reward, 30% click rate. If we show website 2, there's some 30% click rate, 40% click rate. If we show website 3, there's 20% click rate. So ideally, we should be showing website 2. That's what we are learning. Okay. So, and we are caring about regret, and that's what's earning. Okay, if the times you're not showing website 2, you're losing money, and so you're balancing those two. Now, contextual bandit is saying there's a state or a context. Okay? Given a context, the policy will tell me what action to take. Okay, and given that I took an action, that's gonna give me a reward in that context. Okay, so think of a certain user, right? Somebody in mining industry and a male. For them, I show a website with sports. Okay, maybe that will lead to a click, but the click is because they were from mining industry and a male, right? So the context and the action together tell me what the reward is. Okay. So context influences the reward. I mean, if you show sports stuff to let's say somebody who's interested in music, then you will not see that reward. Okay. So the action is not a single best fixed action. The best action depends on what context is coming in, That's kind of very natural. But next time we're going to see a situation where the action you take influences the person. Okay, you show bad recommendations that will change their, they will feel unhappy and they will kind of influence the reward that you would have gotten. Okay, so there's a feedback loop based on from action as well as from actually not sure, from states themselves. Okay, from states also. So if this arrow is not there, it's just a contextual bandit. But if the actions and the states also influence the next state, next interaction, then that's a reinforcement learning problem. Okay, that's RL just means reinforcement learning here, and we're gonna kind of go through this in detail next time. Okay, so yeah, in summary, we looked at we started A/B testing as an idea to figure out decisions, right? But it was actually just learning first and then taking decisions. It was not exploring and exploiting at the same time. But it is actually essentially a randomized control trial, and is a gold standard. But most of the time, you probably not be able to do it. But all the big companies are doing it actually in a very controlled way. So next, more efficient use of user interactions is, in this case, interactions with the environment is through multi-out bandits or contextual bandits when they're context. And contextual bandits are a special case of reinforcement learning. So that's why, so we're leading towards the more interesting, more challenging problem. And really, there's one way to get at least a narrow AI agent, okay? Very narrow AI agent, not a sentient being, but so contextual bandits are a special case of reinforcement learning, and we'll study the second part, reinforcement learning algorithms next time, okay? Yeah. So if you have any questions, come front. Otherwise, we're done.